In this segment, I want to talk about applying Newton's second law and Newton's third law to collections of objects. So I'm calling this interacting objects. Of course, we know that forces are always interactions between objects. So all forces are interactions. But a lot of times we'll have problems where I'm asking you explicitly about the forces of one object on another, and maybe of that second object on the first. So there might be times when I'm asking you specifics about the forces that are connecting objects together. You'll see more about what I'm talking about as we go through this. So if we have more than one object of interest, we can apply Newton's second law to each object separately or to the collection of objects together. And so, we're going to do this example in just a second, but this is just an example of what I'm talking about with interacting objects. Here I'm pushing on this block with my hand, and so I've got my interacting objects are A and B, and I suppose my hand is there also. But that's the kind of situation I'm talking about in this segment. So, again, we can apply Newton's second law to each object separately or to the collection as a whole. And when we're applying Newton's second law to the collection, we ignore internal forces. And so this is another one of those things that we've actually already been doing, though I haven't explicitly stated it. I've said, what's the force on this ball? We've said, the force is gravity when it's in the air. If it's in my hand, I've got weight down, and I've got the normal force from my hand upwards, right? Man, we never talked about the forces that are holding the molecules in this tennis ball together, did we? No, there's all kinds of forces going on inside this tennis ball. There's forces holding electrons to the nuclei of the atoms within this tennis ball. We never talked about that, right? So we've already done this. We're ignoring internal forces. That's what we've been doing. And I guess what I'm talking about here is, what if I ask you about those internal forces? For example, in this problem, what if I asked you about the force of A on B or B on A? So now we could think about A and B together as one object. There's no reason why we couldn't think about it that way. But in this case, I'm explicitly asking you about the force of A on B and the force of B on A there in question B. So we've got to get at those internal forces. That's what I'm talking about. Now we have a collection of objects. We can treat it as one object, A and B together, separately, either way. Let's just do this example, and I think it'll be clearer what I'm talking about. So block A has a mass of 1 kilogram. Block B's mass is 4 kilograms. They are pushed with a force with a magnitude of 10 newtons. Ignore friction. What is the acceleration of the blocks? Okay, well, acceleration of the blocks. And I've been given a force and some mass. This must be a force problem, right? This has got to be. Acceleration of the blocks. Well, I think that in this case, for part A, it's a force problem. Let's just start with our steps. First, we should probably draw ourselves a picture. There's a nice picture. Block A, block B, and I am giving them a push. That hand has too many fingers. There we go. Okay, giving them a push. Okay, there is my picture. Now, it's asking for the acceleration of the blocks. So in this case, it's not asking us to get into the internal forces in any way. It doesn't ask us for A on B, B on A. So, for this one, I think that we should make our object of interest, both of them together. Both of them together will be our object of interest for part A. Well, I drew my picture. I should define a coordinate system. Boy, no reason not to use standard. And then we should draw a free body diagram. Again, the object of interest is blocks A and B together. So that's what my free body diagram should be. We have a normal force. We have the weight. And we might just add a little note here. That's the weight of A and B. Okay, so we've got the normal force and the weight, and then we also have this push, right? And so if I'm here and I am pushing like this, what should we call that? We could call it the push if we wanted. I don't know. If I'm doing the pushing, why don't we call that F, me? That's hilarious. Okay, So there's my lovely free body diagram. Let's go ahead and do, what's our next step? Apply Newton's second law. Now in this case, there's really no action in the y direction. Let's just start with the x direction and see what happens. So the sum of the forces in the x direction equals mass times acceleration. Well, what do we have? We only have one force in the x direction, and that's F me, still hilarious, equals mass. Now what mass? Well, this must be the mass of A plus the mass of B. Why? Because that's our object of interest, times the acceleration. And so you can see that we can just easily now solve for the acceleration. Simply F me over ma plus mb. And so then that is 10 newtons divided by the mass of the blocks. Together we've got a 1 kilogram and a 4 kilogram. Two meters per second squared. Okay, great. So now we know that the acceleration is 2 meters per second squared. A newton divided by a kilogram is a meter per second squared, because remember, a newton is a kilogram meter per second squared. Great. So that's part A. We're done with part A. Maybe we'll add a little note here. A equals 2 meters per second squared. Let's move on and do part B. I guess that part B says, what force does A push on B or B push on A? And now notice that we're asked about forces that are internal to what we call our object of interest. So we can no longer let A and B together be our object of interest, because we can't learn anything about the internal forces of our object of interest. So what we need to do is we need to break it apart. Let me erase my board, and I'll be right back with you. Okay, so now we're back. We've still got me pushing on block A. Block A pushes on block B. Together they accelerate at 2 meters per second squared. Now I'm asked about the internal forces. What force does A push on B or B push on A? Well, now we need to make either A or B our object of interest. It turns out it doesn't matter. We'll get the same answers either way. Since we have to make a choice, I will choose B. B will be our object of interest. Okay, so then what forces do we have? Well, still a normal force. Still the weight of B, not weight of A and B, just weight of B. And there's some force pushing in this direction. A lot of times students will say, oh, well, it's this force of me that's still pushing in this direction. That 10 newtons, right? There's 10 newtons. No, this finger is touching block A. It's not touching block B, right? I am the one applying this force, remember? And I can only apply contact forces. So I am touching block A. I am not touching block B. This 10 newtons is applied to block A. It is not applied to block B. Again, remembering from way back when we first started with forces and our force identification skills, we drew this circle around, and there's no contact forces applied to block B that don't touch that circle, right? So, what should we call this? I don't know. I think we should call it FA on B. Seems like a nice descriptive name. That is my free body diagram for block B as the object of interest. Great. Now we can apply Newton's second law. The sum of the forces in the x direction equals mass times acceleration. So in this case, we have FA on B. That is the only force acting on B, equals mass. Well, we can just plug that in. What is the mass of block B? That's 4 kilograms. Times the acceleration. We learned that in part A. And we get 8 newtons. And I said with what force, right? And so FA on B is 8 newtons. And in what direction? Well, A is pushing on B to the right. Which means that FB on A, So FB on A then must be, well, Newton's third law says that if A pushes on B, then B pushes on A with an exactly equal and opposite force. So FB on A must be 8 newtons to the left. And again, we chose to use B as our object of interest here. We would have gotten the same answer had we chosen to use block A. So another way for objects to interact that we'll commonly see in this class is when objects are connected with a pulley and a rope, or with just a rope. And so this is a picture that sort of shows that setup, the basic setup here. We might have two blocks A and B, again, connected by a string. And in this class, we make the assumption that all strings are massless and cannot be stretched. And so what does that mean? It's not something you need to worry too much about. All it means is that the tension at one place in the rope is the same as the tension at every other place in the rope. You know, in a real rope, if I had a real rope hanging here, it has some mass, right? And so the top of the rope has to support the entire rope, whereas a point farther down only has to support the part that's below it. So in a real rope, the tension is greater on top at the higher points, and it is less at the lower points. We won't worry about that for now. We could if we wanted to, but we're not going to. So this means that the tension anywhere in a single rope is the same, as long as we have a massless, frictionless pulley. So far, we will add mass and friction to pulleys later on in the semester. But so far, we have massless ropes, massless, frictionless pulleys, and that means that a pulley only changes the direction of a force. It does not change the magnitude of the force. So in this case, this pulley changes the direction of the tension from horizontal here to vertical here, but it does not change the magnitude of the tension. And since it's a massless string, the tension in the string everywhere is the same anyway. So we have the tension at this point is the same, the magnitude of the tension is the same at this point. The only other thing to remember about ropes is that they always pull, right? A rope can't push. So here we see, this string is applying a force to the right on block A and upward on block B. So ropes can only pull, they cannot ever push. All right, let's just dive in and just do an example here. So all three 50-kilogram blocks are at rest. The tension in rope 2 is what? Is the tension in rope 2 greater than the tension in rope 1? Is it equal to the tension in rope 1? Or is it less than the tension in rope 1? I'll pause the video. Why don't you try and figure it out? And I will see you on the other side. Okay, well, I think in order to wrap our brains around this, let's just do a quick free body diagram for that 50-kilogram mass. So the free body diagram for the 50-kilogram mass looks like weight down and tension up. Are any of the blocks accelerating? No, they're all at rest, it says. So none of them are accelerating. So that means that T equals W in every case. If T equals W in every case, well, then that means the tension in rope 2 is the same as the tension in rope 1. Why? Because W is the same in all three masses. They all have W equals 50 kilograms times 9.8 meters per second squared. So that's their weight, which means the tension up is always the same. Each block is in static equilibrium, so F net equals 0 on every single block. Okay, so let's do this is a classic 2 blocks with a pulley problem. Block A, with a mass of 4 kilograms, sits on a frictionless table. Block B, with a mass of 2 kilograms, hangs from a rope connected through a pulley to block A. What is the acceleration of block A? Okay, what kind of a problem is it? Well, I hope you said it's a force problem. Indeed, it is a force problem. How can we tell? Well, it got ropes, stuff. It's a pretty good clue. Gave us mass, and it asked for the acceleration. In order for this to be a motion problem and get acceleration, man, they would have had to tell us something else. An initial velocity, a time, right? We would just have to know something about velocity and time or distance. And we just don't know anything about velocity, time, or distance here. The only thing I can possibly think of, the only kind of problem this could possibly be is a force problem. Okay, so this is a force problem. So let's start by drawing our picture. Great. That's a lovely picture. What's our object of interest here? Well, you know what? I'm going to treat them separately. I'm going to treat this as having two objects of interest. Okay, that means we'll need to do a free body diagram for both, and then we'll do some algebra at the end to make it all work out. How should we define our coordinate system? Well, if we just use a standard coordinate system here, like this, then the acceleration of block A will be in the positive x direction. The acceleration of block B will be in the negative y direction. Since our rope cannot stretch, the magnitudes will be identical. So the acceleration of A, the magnitude of the acceleration of A, is the same as the magnitude of the acceleration of B. But with a standard coordinate system, they will have opposite signs. This will have a positive acceleration. This will have a negative acceleration. And there's a lot of ways to deal with that. My personal favorite way to deal with this is to use a non-standard coordinate system. This is in some ways a one-dimensional problem, right? Because these blocks are going to do this. That's it. I mean, I suppose I could pull on A and have them do this. But if I just let go of them, they're going to do this, right? Okay. There's never a situation where it's going to go like that, right? It's never going to be like, or right? That's never going to happen, right? In a way, this is a one-dimensional motion problem, but our dimension has to curve. Let's just do it. That is my positive x direction. So in other words, I'm making my positive x direction follow my string. Can I do that? Sure. Works out just dandy. There's other ways to deal with that negative sign. But one way or the other, you have to deal with the fact that in a standard coordinate system, acceleration of A is positive and the acceleration of B is negative. So somehow you got to work your way around it. This is the way I suggest. You use a curved coordinate system that wraps around the string like that. Great. Let's do a free body diagram for block A. Tension, normal force, the weight of block A. Free body diagram for block B. Tension up, and the weight of block B down. To remind us, in the location of block B, we're using X and Y here. And in the location of block B, we're using X and Y. Again, we've wrapped that X coordinate around our string. Great. Now we have both block A and block B to worry about. So we're still just following our steps for force problems, but now we might have to do X and Y for 2 blocks. We may potentially need to do 4 equations. Some of the forces in the X, some of the forces in the Y for block A and block B. So that could potentially be 4 equations. So you wouldn't want to give up on this strategy until you'd written down all 4 of those equations to make sure. Now in this case, all of the action is in what I'm calling the X direction here, right? Block A will be moving in the positive X direction here. Block B will be moving in the positive X direction here. So that's where all of the action is. So for block A, the sum of the forces looks like, in the X direction, equals mass of block A times A. Well, I only see one force in the X direction on block A. So that is tension equals ma times the acceleration. Now, at this point, some of you might be tempted to give up or feel like maybe you picked the wrong strategy or something because we don't know tension and we don't know A. And so we can't get any farther here, right? But don't give up on the strategy yet. you have two unknowns and one equation. That means we need another equation. And we can get that by doing the sum of the forces in the x direction on block B. The sum of the forces in the x direction in block B. Now this, we have to be careful here. Notice that WB is in the positive x direction. It's in the direction that I called positive. And tension is in the negative x direction. And so now you look at this and you say, oh, now we have two equations and two unknowns. Notice I have T right here, two equations, two unknowns. I have T isolated already. I'm just going to substitute that into right here, and then I'll only have one equation. Substituting in T right here. And now I can solve for A. Bring this term over and factor out the A. Factored out my A, and now I'll divide by the leftovers. WB, you'll recall, is mass of B times G, divided by that equals A. Great, now I can plug in my numbers. Mass of block B is 2 kilograms. Divided by 4 kilograms plus 2 kilograms. And when I run my calculator, I get 3.27 meters per second squared. Okay. Not too bad. So this usually freaks students out when I curve my coordinate system like that. I say, can you really do that? Like, what? And the answer is, yeah, I can. Again, it's basically like a one-dimensional problem. You know, if you had a train going around a curved track here, right? You know, you could treat that really as a one-dimensional problem because the train is either going to do this or this, right? It's never going to do this. That's how trains do it, right? So here's the same thing. You know, we've got this constrained to this track. Well, we could just let our dimension roll along that track. There's other ways to deal with it, right? If we were to use a standard coordinate system, and so let's have a big if we were to here, all we would need to do is just have a third equation that said a sub b is equal to negative a sub a, right? And that's another way to take care of it, right? It's just to be sure you include a negative sign for one of the accelerations. I find students really often forget that negative sign. Whereas I find that students that adopt this strategy, at first it's tricky. It's so tricky though, you don't forget it. And it's easier to remember this in a high-stress situation like an exam. I find that with that negative sign, it's just a really easy thing to miss. So, this is the way that I like to do it. There's other ways.